Okay, now let's go back to R and let's install it. If it is in the repository, it's very simple to install it. So I go to my R window, I clear the screen, and what I have to do, be careful, is install that packages, and then between commas de opt-in, because we learned this name. Okay, let's try to see what happens. Okay, select a mirror. Fine, let's take Austria, as usual. Let's wait. Okay, something is happening. Downloaded, installing, done. Okay, good. It's installed. The fact that it's installed doesn't mean that you can use it. In order to use it, you have to upload the library. So let me give this instruction: library de opt-in. Perfect, we are done. And remember, if you exit from R and you reload R again, restart R again, you don't need to reinstall the package, but you do need to run the library command. Now, the good thing, if we uploaded this function, is that if we make help de opt-in, we find it, and here we have the help. Okay, let's look at the help, which is very easy, because we see that there are only 3 arguments, the other ones are default. So, what is the first argument? Fn. Fn, the function to be optimized or minimized. Good. In our case, it's imod. Perfect. Lower upper. What are lower upper? 2 vectors specifying scalar real, lower and upper bounds for on each parameter to be optimized. Perfect. We are done. And let's look also at the other arguments, which have defaults. But it's better to get an idea of everything needs to be specified. If there are defaults, you can omit them, but let's look. Okay, control, a list of control parameters, CD opt-in control. Okay, let's forget about it for now. Fn map, an optimal function that will be run after each population is created. Okay, it's too detailed, let's forget about it. And further arguments to be passed to Fn. Okay, there is still something that I don't understand here. Does it perform minimization or maximization? We need to learn it. And there is another thing that I want to know. Can I specify an initial value for the parameters? So let's try to understand some more. Because here there are further arguments. And we need to get an indication of these further arguments. Let's see if we have some indication here. Maybe that we need to look at the opt-in control for details, like it's written there. Okay, let's see if there are examples. This is important. Let's just see. Okay. To perform a maximization instead of minimization of a given function, simply define a new function which is the opposite of the function to maximize and apply the opt-in to fit it. And we need to minimize, so I think we don't need to say anything here. And now there initial values. I'm not sure whether we can provide them. Let's see. Okay. Let's have a look at the optim control. I think I'm just looking if there is the possibility to give initial value for parameters. Okay, I don't find it, so let's not lose time and let's run it. One thing I wanted to say, if we run it by using the current function of IMO that we built, there is the plot in it. The plot takes time, so, but gives the opportunity to see at each step what's going on. So I think that we may make a try with the plot, but on the other hand, it is my prediction is that we will have to stop it because it takes too long to run. But let's try. So let's just write something like a name of a variable as a is equal to the optim IMO. Lower is equal to I don't remember. Okay, let's see. Lower is equal to, let's say, 50 for Cmax. Let's put 0.2 for beta, 0.1 for alpha, and 1 over, we may try over 1,000 and 1 over 10,000. This is lower. Upper is equal to C, upper value for C, 400, upper value for beta, 0.8, upper value for alpha, 0.9, upper value for K, we can make 1 and 1 over 10. You can't see on the screen, but okay, let's see if it works. Yeah, you have a question?
Yeah, it's not required a C after lower equal.
Yes, correct. Correct. Okay, let's see if it works. Yeah, it works. Now let's go to the graph. You see the attempts. It is trying. Okay, now we could leave it running, and my prediction is that it may take a couple of hours to conclude. So at a certain point we have to stop it. But you see that there are different results. And there are some of them that are quite good indeed. What we can understand from here is that it's difficult to get both, this is not bad, the last one, it's difficult to get both high flows and low flows well predicted. At the end of the story, it will be retained one value, which is that corresponds to the best sum of squares. And what is also interesting is that while it is progressing, you should see that it converges slowly to a good simulation. So for now, you are still seeing some very wrong ones, like this one. This one is also wrong, this one is wrong, this one is not good, this one is already a little bit better, this one is wrong, this one is completely wrong, this one is not bad. So you see that there are still some simulations that are completely wrong. And while it progresses, it should converge to better simulations. And you understand it because so far it's still in the first loop. The first loop means that it's still trying over the whole range of parameters. And in the second loop, and it will write down on the screen when the second loop starts, it is restricting the range based on the results of the first loop. But we are still in the first loop. Okay, let's keep it running for a while. Okay, you see this is the completion of the first loop. And you see that there is a best value of the sum of squares, which is, I think it is already better of our best value. And at the end of the loop it says, what is the best value? It's 1,384,000, and the best values for the parameters, you see? And now, if we look at the graph, we should see a slight improvement. It's still in the second loop, so the improvement is, yeah. We see that there is already some convergence. Still, there is some simulation that is quite wrong, but with respect to the previous loop, this is wrong, for instance. With respect to the previous loop, we see some improvement. And we have the problem of the red line. I didn't solve the problem of the red line. I didn't extend it up to the end of the graph, because you remember that I had the problem, the error. But okay, this, you can solve it. It's easy to solve. But still, it is quite fine. The previous one was not bad. This one is not good. This is not good. This is wrong. And yeah, this is not bad. The second loop is concluded. And let's look at the result of the second loop. I think you can set the maximum number of loops. Now it's 20, I think. You see that the best value of the iteration is not changed much. No, it's the same. I don't understand why. It didn't change, and also, yeah, probably because during the second loop it couldn't improve the parameter values of the objective function. But you see that there are some simulations like, you see, this one, this is not bad. Or, yeah, this is not so good, not so good. This is not bad, not so good, not so good, not so good.
But with these results of the iteration, we should get all the same numbers.
You mean all the same numbers? What do you mean?
Those values for the parameters and for
Yeah.
because I have different numbers.
No, you don't get the same numbers. Yeah, no, you don't get it. Because, you know, when the program starts, it randomly searches for solutions. It's not a deterministic search, it's random. And different computers have different random seeds. Random seed is the seed for the generation of random numbers. So it's different. This one is not bad. And now there was a third loop. Let's see if we got some improvement. I don't understand. It looks like it is repeating, which is strange. It's repeating the same result, which is strange. And I wonder whether it does it happen also for you, or repeating the same?
Yes, I mean the 13th iteration and the last quarter all the same.
last four.
No, no, also the, I don't know, a couple, like.
This is a bit strange, and I wonder whether there is a mistake in the computation of the function. I don't think so. And what we could do is, let me check. I'm waiting for the fourth one, because it seems that it is converging, but yeah, now it is changed. Now it is changed, so it may be that indeed it is not much changed, but we can see some change. This is not bad. Okay, anyway, I don't think we can... Okay, we stopped it. Okay, that's it. Now, my proposal now is, let's assume that you understood it, and my proposal now is, let's try to in order for you to learn how to independently perform a similar procedure, let's try to make an exercise together. And the exercise may be, let's try to write another code which is a linear reservoir code. Let's fit on the same data set, and I think we could make a simplification by assuming that evapotranspiration is 0. Let's fit on the same data set a linear reservoir. And my proposal for you, we have about half an hour to go, some more probably. And my proposal for you is let's try to fit a linear reservoir here. By writing a new code in the form of a function. Okay? And I think we have enough time. Okay, so let me go back to our code for iMod and let's open a new window. And let me write something like linear is equal to function par. Good. My suggestion is that you move forward with me, if you can. What is the purpose of making this simple exercise? This is, the code is very simple. It's much simpler with respect to iMod. And the purpose is to check whether you are able to independently make an exercise that is simple but based on the same concept. If you get the concept, then increasing the complexity of the model is a straightforward step. Okay, first we need here a curly bracket. And let me say that in order to make things different, our parameter here is just k, so let's just use k. Okay? Okay, first let's assume that we have rainfall in the form of a vector that is named p. And the first thing that we have to make is to write a cycle to perform the simulation for I in 1, 2, 8, 7, 6, 0. And then a curly bracket. Now, the first thing, remember how the linear reservoir works. It's a tank. And It's a time, so with the storage W changing in time, array for P is a function of time, and here we have a Q, which is a Q time, which is equal to W time divided by K. In this case, K is a time. Let's take it as a time, okay? Perfect. Let's say that EP is 0. So EP is neglected for simplicity. Okay. Of course, it will be highly uncertain if we work with this server data, but let's try to do it. So first of all, at each time step, what we have to do? We have to add to the storage rainfall, and once that we computed the new storage, we compute the outflow. And then, at the end of the same time step, we have to subtract from storage the outflow. And so let's try to do it. First, before starting with our cycle, let's set W equal to 0. And then we go with our cycle. So W is equal to W plus P. But be careful, it's Pi. Now we have to write Qi is equal to W divided by K. And now we have to take units into account. So W in millimeters. Qi, we need to make some conversions here. And let me write it here. Qi is equal to Qi. Conversion because K is given in seconds, and that's fine. And but W is in millimeters. So if we want to compute the flow in cubic meters per second, we have to divide it by 1000. We get to, in this way, we get to meters. And we have to multiply it by the area of the catchment, which you remember it was this number. And this number in square kilometers was 1214, and then we have to add 6 zeros. I think this is fine because then K is in seconds already, and therefore it should be fine. Okay. Now, before making the conversion, it's better if we subtract W is equal to W minus, we have to subtract Q. Let me think about it. Let me think, okay, I think minus Qi. I think this is fine because but the time step is we need to multiply it by the time step. The time step, our time step was daily. Yes, it was daily with the data we are dealing with, or it was not daily, it was hourly. So we have to multiply it by 3,600. I think in this way should work. Because basically Q is expressed before converting it is expressed in millimeters per second. And therefore, if we want to compute what is the storage decrease due to outflow of Q, and the storage is in millimeter, we have to multiply Qi times the time step. The time step is hours. It's hours because it's 1 year of simulation, 8,760 data, which means hours. So this is basically our computation. And then I think we should put a control here. And the control is if W less than 0, W equals 0. In this way it should work. And I think we should put another control here, which is if Q is greater than 1 million, let's write Q equal 1 million. So we can't allow infinite values for the river flow. So let's put a control to make sure that we don't get any infinite value. Okay, and I think that Q cannot be lower than 0. I think we can write our closure here of the fourth cycle. Now we have to compute the sum of squares. So, in order to compute the sum of squares, we have QOS is simulated. So, I think sum SQ is equal to QOS minus Q squared sum here. QOS minus Q squared. Okay, and then we can write return sum SQ. And then here we close the curly bracket. Questions on this? Because if you don't have any question, I save it. And this is linear.r. And then I try to upload it. We don't have the plot here, but let's try to run it. Questions? Okay, let me try to run it. So, let's clear the screen. Source linear.r. Okay, it was uploaded. Now if I write linear, there is the function. Let's try to run it. And let's try to make linear of, let's give a k value in seconds, 3, like this. There is an error. Let's try to see why is that. But first let me try with another value of k, because I want to make sure that it's, I think it is a general error, not related to the value of k. Okay, so let's see what happens. No, it should not be a problem. Let me try with another value of k, because I don't see the mistake. it's here, it's here. Ah, yeah, okay, I understand. We need to define Q. Sorry, Q. We need to define Q. Q equal ref 0, 7, 6. I forgot to define the vector Q. You remember that we need to define vectors before using them. Okay, I did it. Now let me re-upload the function. And then let's try again with this. Let's see, there are warnings. Let's see what are them. Yeah, okay, sorry. I forgot this. If Qi here is greater than Qi. Okay, good. Let's see if we are okay now. Okay, now it seems fine. And let's see what is the result. This is better. Let's see here. This is even better. We don't have the plot, so we can't check. But let's forget about the plot for now. And let's see if I add another 0, probably there is not a big improvement. Okay, now let's now apply d-optim, because our purpose is with a simpler function to see whether we can get to optimization. But be careful of what I'm saying now. We have a problem. We don't have a problem. We want to make a test. So the purpose of this exercise first is you asked me a couple of weeks ago, Niccolo, you asked me how to write the linear reservoir. So first, this is the code of the linear reservoir. This is a very simple code. And now, I want to make a test, because if we work under uncertainty, we don't know whether we succeed in our optimization. And we always work in the real world under uncertainty. There is a limit to the performances of a model. But let's make a test. Let's put ourselves in a situation where there is a perfect solution. And let's see if we can't find it, if we can find it. So in order to get a situation with a perfect solution, we need to forget about the observed data and adopt as observed data a simulation from the model for a precise value of the parameter. Okay, so if I run the linear reservoir with a k equal to 100,000, or let's say 10,000, I run the model with k equal to 10,000, I get a simulation. Let me adopt it as observation. Okay, so in order to do that, I need to change the function of the linear reservoir just for one time, and I need, sorry, this doesn't, let me remove this graph, and I need to change it here, because I don't want to return some SQ, let me return Q, okay, in order to get back the simulation. Okay, good. I go back to R, I need to re-upload the model, and then let me write QOS is equal to linear and 10,000, the parameter K. Good. Let me see a plot of QoS to see if I got a reasonable result. Plot QoS type equal line. This is my result. It is not very reasonable. It looks like something that needs to be smoothed more.
So
Because, yeah.
is it possible to scroll down?
Ah, yeah, sorry. I'm sorry for that. Okay, good. Sorry, I forgot that I brought the screen up. But if we look at the diagram, let me see. You see that it's not very reasonable because it's too spiky. I need to smooth it. And in order to smooth it, what I need to do is to increase K. So let me put it at 50,000. Plot. Now it's more reasonable, but I think we can increase it a bit more. 80,000. Okay, now it's fine. And this is my